Okay, we let's check it the theorem precisely. Theorem says, suppose that C is a simple closed contour describing the counterclockwise direction, and second, CK are simple closed contours interior to C, all described in the counterclockwise direction, clockwise direction, okay, opposite direction, that are disjoint and whose interiors have no point in common. Okay? Then, if a function f is analytic on all of these contours and throughout the multiply connected domain consisting of the points inside C and exterior to each the circle CK, then we have this result equation, integral along to the contour C f of g dd plus summation k is equal to 1 to n integral along to contour ck f of g dg is 0. So we use this theorem to our case. Then we have the result here, because we have considered ck, so integral along to the circle C, contour C, k, f of g dg is equal to 2 pi I times residue at the singular point gk. For each k is 1 to keep going n to n. Then we replaced this part by this. Because this part is equal to 2 pi I times residue f of g at gk. Okay, so we get the desired result. So the proof is done. Okay, to see what the theorem says, let's check the example. Let us use the theorem to evaluate the integral equation 2, given expression 2, integral along the contour C, 5 times g negative 2 divided by g times g negative 1 dg. Okay. Here C is the circle, absolute value of g is 2. Okay, here the contour means the circle, given by this, absolute value of g is equal to 2, described counterclockwise. The integrand has, we can see that integrand here has the two isolated singularity, that is, the point g is 0 and g is 1. And both are interior, placed in interior to C, because we consider this contour the radius of 2 with the center is origin. So when g is 0, here we have here, and then when g is 1, then we have the point here, interior to this circle. So we need to compute, to evaluate this integral, we need to find the residues b1 at the singular point g is equal to 1 and b2, residue b2 at the singular point g is equal to 1. The first two, we are trying to find the b1 by using the Maclaurin series. Here I wrote it. 1 over 1 negative g is equal to summation n is equal to 0 to the infinity g to the n, where the radius is 1. So the validated condition is absolute value of g is less than 1. Here we have the point 0 as a singular point. We consider the this region. We need to modify the integrand here given by this function fg of f5g negative 2 divided by g times g negative 1 into the left function here 5 times g negative 2 divided by g times negative 1 divided by 1 over 1 negative g, and then the first part can be rewritten by this 5 negative 2 over g times the second part here. I can have the Maclaurin series by using this expression here. Just multiply by negative 1 here. We get this. And then further expand the terms, term by terms. Then among them, we can get the coefficient of 1 over g. Here look at that. For the case of 5, there's no term of 1 over g, but by 2 over g, we can have, when multiplied negative 2 over g times negative 1, we get this 2 over g. So the coefficient of 1 over g is 2, okay, in the product. So we got the b1, which is equal to 2. Next, we compute b2, residue b2 at the point g is equal to 1. In this case, we need to consider the expansion whose center is 1. So we need to modify the given function f5g negative 2 divided by g times g negative 1 is into the left hand side here function, quite different from the first case here. The first part is 5 times g negative 1 plus 3 divided by g negative 1 times. The second part is 1 over 1 plus g negative 1 here. Which is exactly 1 over g, but by adding 1 and negative 1 here, we rewritten into this function, and then we apply the Maclaurin series given by this. In this case, we replaced g by g negative 1. Then we get this. Here, look at look at the formula here. Function 1 negative g, but in this case 1 plus something, so we need to consider 1 negative g negative 1 here. Then we insert this term in the variable g here, then we get this. Okay, and then expand the terms to find the coefficient of 1 over g negative 1 over g negative 1. Okay, look at this here. We multiply these two terms, then we get this 3 over g negative 1, which has the coefficient 3 here, which exactly B2, what we want compute. For the second part here, so we found all the residues B1 and B2. B1 is 2 and B2 is 3. So we add these two numbers and 5. We get 5 and times 2 pi I. Then we get this 10 pi I, which is the answer to the example. Okay, we are going to look another method to evaluate the integral, which is simpler. Actually simpler. We write the integrand as the sum of its partial fractions. In other words, this function integrand can be modified into this. There is the sum of its partial fractions, 2 over g plus 3 over g negative 1. Okay. If you want to check whether this equality holds or not, just the both sides you compute and then compare them. Then since 2 over g here is already a Noether series, when we consider the annular region, absolute value of g is greater than 0 and less than 1. And the second part here, 3 over g negative 1 is a Noether series when we consider the annular region, the absolute value of g negative 1 is greater than 0 and less than 1. So it follows that the integral can be computed by adding these two terms, 2 pi I times 2 plus 2 pi I times 3, which is equal to 10 pi I, which is quite simple. Okay.